Hello again. I'm here to continue my last presentation on the discussion on operation of potted ships using our SAMMON planning tool. And you might remember the last time I was talking about the comparison of the conventional operation of pods like a twin screw vessel or the new pod strategy with in-out configuration. And my focus was on efficiency, and there was a lot of discussion afterwards, very interesting. And originally I planned to go onto the stern first method, when the ship is going astern. But I also invited, if somebody has some other ideas for topics, you might let me know. And so some of you did, and therefore I switch into my original plan another topic, which is on the simplified vector approach to estimate or use pod forces. It seemed to be so important that I said, okay, why not having it before we start with the stern first method? When I talk about this, I only talk about ships going ahead, forward motion. And the stern motion comes then with the next topic. Okay, so let's start. Simplified vector approach for pod forces, making headway. What will be unique, specifically our SAMMON, as you always know, and a lot of content. So the first part is, I would like to explain and introduce the simplified vector approach to get the resulting steering forces. And the idea is how you could use your pods that you can create resulting thrust in any direction. Simplified means there are other effects involved which might not be considered if we use a simplified approach, and I will let you know some of these effects before we afterwards step into a lot of sample discussion for manoeuvres using different pod configurations. And I want to be, how to say, a little bit structured. So in the first one, I'm using a ship or the pods only from a stopped ship when the ship is making no speed. And later on, I add some samples if the ship is moving ahead again. Okay, let's start with the first, an introduction. As an introduction, I would like to show some typical configuration for pod. For instance, here is the so-called T-bone, because one pod is showing in this direction, the other one is pointing in this direction. So this is the vector, the resulting vector of these both forces. Then there is the in 120, out 60. So these are the configurations, and this is the resulting vector. And this is the so-called toe-in. If both of the pods are turned inward, I have shown that in my last video extensively. And the same here, so it's a neutral position. If the pods are turned further inward, then there's no resulting thrust, only a little bit if you modify this configuration a little bit. So the challenge and the question is how to adjust the pod angle and the revolutions to generate resulting thrust in any of these directions, in a certain direction and with a certain power. So using a so-called simplified vector approach is very advantageous. So the magnitude and the angle of each pod thrust vector is used to form the total resulting vector. But this is a simplification, and we will show why. Simplification means only the active thrust is taken according to the pod propellers engine order telegraph settings, because these are numbers which you can use, or even RPMs. And these will be considered to form the vector diagram, as you see here. that means something is not considered. For instance, the interference of two pots, if they go into each other like this, if one pot is blowing into the other, then these effects are not considered in this vector diagram. Then the thrust vectors will be considered to act at the ship's center line. Normally, between the both pots, there are some distances, so they are located not on the center line. So they would have generate a lever. We call it shoulder effect in German. Maybe it's international. And what I mean is, we are considering the vectors to attack at the ship center line, so you can easily think about a simplified vector approach. And then there are also on top passive forces of the pots. For instance, if the pot is working like a rudder-like structure, so this is not considered in this vector approach. So simplified vector approach, what does it mean? What is simplified number 2? It means, on one hand, there are the pot propeller forces. They are generating a thrust. And you see it has two components in X and Y direction. This is the longitudinal direction of the ship center line. And normally the thrust points in the direction of the pot angle. But there are also effects. If the inflow to the propeller is not directly as we see it here, then there might be an angle and also an effect on the magnitude of the thrust vector. But this is neglected here. The second one is the pot housing. This here, the strut, it generates lift and drag forces like a normal rudder, because the shape is like a rudder. And this has the components in X and Y direction and forming a resulting force vector from the rudder effect. And both of these components goes together to get the resultant thrust. So it's on one hand the magnitude and the angle of pot forces forming the resulting thrust. So this is this component. Then we have the resulting rudder force vector. This is this one. So this vector goes into this one, and this forms the resulting thrust, even including the shoulder effect of the two pots working behind the vessel. Normally the thrust forces are mostly bigger than the other effects, and so we therefore can draw the conclusion that the simplified vector approach works quite well, specifically in conditions where the thrust pot forces are dominating the other effects. Now we'll show some typical configurations of the pot and starboard pot angles here, and this is the thrust. I will leave this thrust at 100% that you can better see what happens. And I will change some of these configurations and you will see the outcome here. So this is now the demonstration of the pot vector approach. So we have here the tableau for input of the angle of the pot angle and the engine order telegraph settings. Here we see the position of the pots, and here the vectors are shown. So for the time being, it's port 0 degree and starboard 30 degree, as you see here. And both with 100%, then we see better the results here. Okay, what we see here is, for this configuration, 30 degree, or the resulting vector points in 15 degree, and the length of the resulting vector is nearly double of the single pot version. If we go here also to 0, so 0, then we see, okay, so the length is now 200, that's the double of this part. Okay, let's go back to 30 degree, then we see it's now 193. It's nearly double the one. If you go to 60 degree, then we see, oh, it's only 75% of the sum of both of these engine order settings. If we go to 90 degree, so the 90 degree difference between both pod angles, so about 75% of the sum of both remains. It's 150% of one pod, so to say. And if we go to 120, then we see, okay, now if the difference between both pod angles is 120 degrees, then the length of the resulting vector is the same as one of the pods. So this is the combined force, but it's only the force of one pod then. If we go to 150, then we see now it's only half of the force of one pod. So there's a lot of force which is, how to say, wasted or neglected. Okay, so the normal configuration we will show is around these 30 degrees or 60 degrees, and this one 120 degrees. So these are the typical configuration we will show later in the samples. Let me explain one for the toe-in configuration. So 90 degree on the port side and minus 90 degree on the starboard side. So what we see here is the resulting vector is 0. So this arrow is nearly not to be seen anymore. But if we change it a little bit to to minus 80, then we see, okay, now the force which is generated is about 17%. If we go to 70, then it's minus 70. It's about this configuration. So if the pods are working against each other, and this one is a little bit forward, then we see a small thrust force is existing. Okay, this will be used for the next samples. Okay, I will show some samples for to use the SAMMON software, and I will first start with the stop chip, and only one pod is working. This has some advantages because with only one pod working, the other one with no thrust, the total resulting vector is the one thrust force from that only one. And I will show some samples. First, from only the pod port is working, and we will start with the pod in single mode, so to say, and we will always use the in mode with different angles, and then with the out mode showing the effect of so-called forbidden ranges. If one pod is blowing onto the other, we should not consider this effect. So here we are. The SAMMON planning tool, we use it very often, is here the operational panel for using the pods and thrusters and whatsoever we might need. We have here a passenger vessel with 2 azimuth propulsion systems. Here I adjust the propeller, and here we can see every second of this time slider, how it will be acting second by second. Okay, so for the time being, no thrust, both pod angles are 0. And I would like to start now with the thrust. If I increase the thrust, so 1, 2, 3, 4, 5%, 7, 8, 9, nothing happens because it's below the minimum revolutions. When I go to 10, okay, now it starts. The engine starts, and we can see here the shape of the ship's position for the next 20 minutes. And if I use the time slider here, and we will move it as a reference to about 600 seconds. So that means where the blue shape is, I can even blow it up a little bit, with 10% ahead, so that's a minimum revolutions. If I bring it to 20%, then we see, okay, the ship is accelerating much more faster, only with one pod, you see? And what we see, the ship is not moving ahead, straight ahead, because what we already explained, the so-called shoulder effect. So the port pod is a little bit turning the ship because the starboard pod is not working. It's only working like a brake, so the ship is turning in this direction. So this is the shoulder effect. And I also mentioned the so-called rudder effect. So for instance, I make it now a little bit bigger now. So if I use, for instance, the starboard pod, only with no thrust, only the rudder, then we see, okay, it changes a little bit more. So the ship is turning a little bit more to this side, only to the rudder effect of the pod, which is not working with thrust, no generating thrust. This is what I wanted to explain as a simplified version if we only consider the thrust forces. So there are some forces aside in parallel to the others. Okay, this is the introduction. And now we want to really start. I switch off the rudder here now. So this is only one pod working. But if you see what I mean, dominating thrust force, then I will go with the pod to 5 degrees, and then it's immediately succeeding the shoulder effect with only 5 degrees of rudder. If I use, for instance, 10 degree, 20 degree, like this, then we see clearly that the ship is turning very fast, and now we have only 15 degree. You might go more to maybe 30 degrees. So in this case, we know 30 degrees is the pod angle. This is working with 0, so the resulting angle would be 30 degrees. Okay, if we go further, then maybe to 40 degree, and what you see is, and you might wonder, the pod clearly is creating a force to this side, to the outside. So why the ship is turning then to the port side, to the counter side? You might remember my movie about the turning circle dynamics, where I explained the ship is turning to this side because of the lift forces due to the drift angle. Lift comes from the aeroplane dynamics. So if a wing is going like this, and then we have a lift force heaving the plane up. We have now here the ship in the vertical plane. So if we have a lift force from here, then the ship is pushed into this side. So this motion comes from the effect of the drift angle. And you see the drift angle is very big here. Okay, when we blow it up further to 60 degree, now maybe here, so we see the ship makes not a turning circle anymore. The power here at the pod is so big that the drift angle gets so big that there's no lift force anymore. It's only like a resistance. And so the ship is turning nearly on the spot. So this is, for instance, a sample where you can have immediately the resulting pod force is pointing to 60 degree, and we go with 20% ahead. We could also bring it to 120 or others. I'm using it now for 120 degree. We see that for a resulting pod force, to 120 degrees, the ship starts pulling astern already, because the pod is already creating a force astern. In this case, we use always the port pod. So it's in the inward configuration, inward. Normally we could also use this pod for smaller angles. So if I switch that to 0, then it's the same to the other side. But if I'm using this pod now, so it works in the same way as before. Even for the 60 degree, it looks like this. But if we go for tougher configuration, then we see the force is not the same magnitude as we had before. So the ship is not reacting properly on the same angle of the pod. This is why the pod is now blowing onto the other pod, or also a problem to the skeg of the vessel, to the aft part of the vessel. So this is not good. It creates interferences, and we should normally avoid. Some manufacturers even switch the pod off for these configurations. So don't use a pod in this configuration as we see it here. It makes no sense, and it might destroy some of the parts there. Okay, let's forget it immediately. Okay, this is something we could explain for only working with one pod and for the ship at rest as the initial situation. To sum it up, these were the samples we have shown, and now we have to draw a conclusion. And the conclusion is adjusting the pod angles and the revs helps to generate an easy adjustable resulting thrust force in any direction. If you only use one pod, then you don't have to calculate, you immediately know this is my thrust direction. Although this is limited to the thrust if you only one pod. If you need more thrust for a certain situation, then you need the other pod as well. And then you have to use the so-called vector diagram. And this will be shown in the following section. So the next one is then the discussion of two pods working, again for the stopped ship first, with zero speed. If the pods are working together in the same direction, then the total thrust is the sum of these both vectors. For two pods working in an in 120 and out 60 configuration, for instance, resulting in a total thrust direction of 90 degree. So you can use this vector diagram from the port pod and the starboard pod. It's a screen. We can get the black resulting force. And we will use some samples now afterwards with the SAMMON planning tool. And the idea is to compare two samples, for instance, with resulting force angle of 90 degree, but with different pod angle configurations. For instance, if you use the pod, the single pod, and you are now using the two pods like this here, then we need to get the same result from this one. We would need an adjustment of the thrust, because if we leave the same thrust as for the one pod, then the total vector would be too strong. So we might need an adjustment. And for higher resulting force angles, so if you want to create a resulting total force more pointing to the aft, then it might be of some advantage if you turn one pod to a stern mode and the other one then in the in configuration to create any desired angle of the pod you might need. Okay, now we are looking for some samples. We want to start now to compare a simple maneuver with 90-degree resulting pot force, once with one pot and second with two pots. So using this, for instance, to 90 degree, it would look like this here. This is 90 degree. So we see the maximum turning speed is 11 degrees per minute. And this is the position after 600 seconds. And the last shape here is after 20 minutes. Sorry, 600 seconds, it's 10 minutes and 20 minutes. And this we want to compare using both pots, but with the same angle of 90 degree. For this reason, we could use it with 120 degree and 60 degree. Doing this, we have now 120, and this also with 60, like this, but also with the same thrust. And what we see is, oh, the ship is turning a little bit faster. So the turning circle is nearly the same, but it's turning faster because the resulting force is bigger, as we have seen already in the picture before. So we have to adjust it to maybe 17% or maybe 16%. So then the picture is the same as we had for the one single pot version with 90 degree resulting thrust angle. Okay, so if you want to use the ship then in a situation that the thrust will be needed, the thrust vector, resulting thrust in this direction, then we could not easily go with this one to high angles. So maybe with 90 degrees might be the maximum. Then you are blowing already a little bit against the skeg. And this one would be further up. So this would be going like this. But this is not good. For this reason, it would be better to use this pot also with 180 degree, like this. And then you have the chance to verify the angles like using this one. So now it's 106, 150 and 180, so it's 165 resulting force angle. Or if you want to go to the other side, you could easily adjust it with this port. So this would be the best way, going astern and steering the vessel. But this will be the focus of the next movie. Okay, the next chapter and the last one is now about the toe-in configuration. So that means the pots are working against each other. So the total thrust vector, the black one here, can be made to 0 or even very small. So it's very sensitive. The good thing is, starting specifically from 0 speed allows very easy adjustment of the motion. That means both for speed and also for the direction, even with less effect than the minimum revolutions. So this is the most important application of this method. And from higher speed, the pots can, apart from other steering effects, can create tremendous resistance to stop a ship much faster than with a normal propeller mode. The samples I will show with the SAMMON planning tool, these are maneuvers from stoppage ship first, and I will start with in 90, slowly moving the ship ahead, turning the pots a little bit in the forward direction, and you will see the effects. And also, this might be a little bit strange because nobody talked about that. You can use this toe-in mode also instead of in the transverse direction. You can also use it in the longitudinal direction. This would mean one pot is pointing astern and the other one is pointing ahead. Although this can be used very efficiently, you can even use it for crabbing and for slow motion. And if you use the thruster difference here of these bows, you can move the ship in longitudinal direction. Okay, and the final thing will maneuvers from forward motion, so in 60, 70 or even in 90 to stop a ship very quickly. What I wanted to add is a comment that means these maneuvers should only be used, this configuration, if it's really necessary, because working with two pots against each other is a waste of energy. So please think about that when you steer your vessel. Okay, so let's look for the samples. 10% is the minimum engine order telegraph setting, so the revolutions in about 15 revolutions per minute. And you see after 10 minutes the ship is going with 1.45 knots, so it's quite fast maybe for some of the applications. But you can't go with less RPM. If you reduce it like this one, then the engine will not start, will not turn. Okay, so the idea is, for this reason, use the pots with 10. No, better. We switch off the pots like this, so the ship is at rest. Then we move the pots both to 90 degree toe in. So this is 90 degree to one side, 90 degree to the other side. So this is 90 degree, both of them. And then we start the engines. This is both engines now with 10. And if you want to start the vessel now, then you could use it maybe only with one pot. Then you see the ship is very slowly starting moving with 10 degrees. So like this, for instance, if you use also the other port, then the ship going straight. If you use one pot more than the other inward, then you see the ship is turning. So this can be adjusted to any speed you need. So this is now half a knot only, and we go with 10 engine orders, or minimum. We can go very, very slowly and can adjust that the speed. Crazy questions. Can we also use this toe in, not in this direction, but in this direction? You know what I mean? If I'm going this ahead, and this should be going astern, like this. So what you see now is one pot is pulling the ship astern, and the other one is pushing the ship ahead on the starboard side. So you see immediately the effect that there's a turning effect because of the shoulder, you know? And if you increase the revolutions ahead, then this turning effect will be bigger, 30%. So this is a turning only by the shoulder effect. What you could use is then to say, okay, I will use this pot on that side a little bit to create a thrust in this direction. So you can adjust it in a way that you go 10 degrees, for instance,
12 minutes. So this is
we
double.
can really use the ship for crabbing. So sideways crabbing. If we also adjust a little bit the forward or direction, then you see that you can really adjust and move the ship in any direction you would have. So just in case, if your bow thrusters are out of order, then you might also try crabbing with the ship with this toe-in configuration in vertical direction. And the next will be talking about the moving ship. So the next chapter is now the use of two pots in in-out configuration for the moving ship. So we are now moving with a certain initial speed, using, you can use the same methods as we have used before in the same way. When the vector starts from non-zero initial speed, then you will see, by means of the samples to be shown, that the effects and the tracks shown before at no speed, now all the track is moved and shifted in the direction of the forward motion. So it's very easy to keep that in mind. The samples I will show with the SAMMON planning tool will be first maneuvers from initial speed of about 7 knots with the engine order settings of 30%. This is the steady state speed for these settings. And first we will use one pot only for comparison with the others. And then 2 pots in sync mode, so both of them are turning 30 degrees. This is normally some kind of reference maneuver in the IMO maneuvering booklet or wheelhouse posters. And I will also show some other configuration with 60 degree, 90, 30 and so forth to show the effect of these different angles. And on top, I will also increase the thrust, so-called kick turns, to see what effect we might get with this measure. For the smaller and bigger angles. And we might also have a look reducing the thrust on one pot and also the effect if one pot is, so to say, in a braking state, what that might be for the turning motion. So these are now the experiments with the moving ship and with 2 pots. The ship starts here with the engine order setting 30. Both pots are working ahead, 0 degree. And we first start with turning. Let's start with one pot to 30 degrees. This is now 30 degrees. So it's with one pot. And so you see the ship is turning quite fast. And if you use also the other pot to 30 degrees, then the turning circle increases even more. And this might be the normal reference turning circle for 30 degrees of rudder, 30 or 35 degrees of rudder. We will make that as a reference here in a other color. So this is the position after 6 minutes, and this is the position after. Okay, now we can try out some other configurations. For instance, if we go with both pots to 60 degree. We can even synchronize the pots, and we see they are both working in the same way. So this is now the situation we have nearly seen also when the ship was stopped at the start. So the ship is turning heavily, and the transverse forces of the pot are even turning the ship finally on the spot. So that's what we have also seen. But as I said, the turning circle is a little bit moved in this direction. So what can we do further? Maybe we use the inner pot to 90 degree. Maybe you can achieve a little bit more turning. So the idea is, what is the smallest advance of the ship in ahead direction? So the ship should not be going too far away in this direction. Okay, this is with 90 degree. If we reduce this maybe to 30 degree, so we see the lift force is bigger if we only use 30 degrees. So the ship is a little bit moved to this direction. To go with this pot to 120 degree. So this would be 120. and this could be shifted to 60 degrees. So the ship is not moving so much forward anymore. So you see there's a turning speed of 24 degrees per minute, but the ship speed at this position is only 1.23 knots, so it's very low. The idea is now, or the question is now, how can we reduce the swept path in this direction? Can we even make it a little bit more efficient, the turning? And for this reason, we could use a kick turn. For the time being, we are moving with 30% of engine order, but when we blow it up, for instance, like this, so to maybe to 50 or 60%. So this is now 60% on both engines. So what you see here is that the ship is already turning here. If I move it a little bit back, then you see 60, this is after 1 minute. This is the turning of the ship here. It nearly stops. So at this position, only the stern swings out heavily. So if we play a little bit around with the pots here, if we go to 120, so we see that the ship is, with the resulting pot angle of 60 degrees, we are coming to a halt in this position. This is a maneuver, a kick turn on one engine with 120, so therefore the ship is really come to a stop nearly here, and the other one is set to 0 thrust and zero angle. So what have we learned from this one? So this would be a thrust angle of 120 degrees, because this pot makes no thrust anymore. So a pot angle in this direction creates, how to say, the fastest turning and stopping, the least advance, at least for this ship, for this simulator ship. This is now the final discussion on toe-in maneuvers. And this time it's a maneuver with SAMMON starting from speed. So the ship is in motion. You see here is the bow of the ship, which is moving with the speed of 13.5 knots. And we want to stop the ship and turn it a little bit, and only to demonstrate how it's being done. So this is in maneuvering point number 0. When I go back, go further in the plan, this is now at maneuvering point 1, where I stopped the ship. The engine order was reduced from 60 to 20%, and additionally, both pots were turned in to 90 degrees. So what you see is that the ship is losing her speed, so the shapes are squeezed together, and at this position, it's only by braking, by using the pots in toe-in position. Here at this position, the speed has already dropped to less than 1 knot. So this was this maneuver. And here the pots were a little bit changed. So only the starboard pot was used only from 90 to 80 degrees. So it gives a little bit a kick, because the vector is now moving a little bit in this direction, only very short resulting vector, and so we see that the ship is slightly moving in this direction. This should only show the effect of these braking effect of resistance of the vessel, and also the use of the toe-in configuration to steer the ship a little bit. Okay, thanks a lot. Oh, sorry, this was a mistake. It should be a secret, because this will be the topic of the next movie.